In a crisis, a green light on a digital interface means absolutely nothing if the physical hardware fails to move. A software status cannot stop smoke. Only solid steel and massive volumes of moving air have the physical capacity to push back a toxic hazard. A commanded digital state is an assumption. Until a current sensor trips or a damper and switch physically engages, the control panel is simply guessing. True safety requires explicit, independent mechanical feedback. Securing that physical proof requires specific survival ratings. The exhaust fans executing these commands are built to withstand temperatures of 250 degrees Celsius for 2 full hours. The air delivery system itself must withstand intense internal pressure. That means installing SMACNA Class 3 high-pressure tracking ductwork wrapped entirely in thermal fire-rated insulation to prevent structural rupture. Simultaneously, heavy-duty actuators are deployed to forcefully stroke massive control dampers fully closed in under 15 seconds, completely sealing off compromised zones. Relying on a digital run status without these physical guarantees creates a fatal false assurance. When a building's software says it's safe, but its hardware is failing, a fortified structure becomes a locked trap. During normal operations, data center ventilation systems operate under strict energy efficiency mandates. Facilities optimize their equipment to keep their power usage effectiveness, or PUE, as low as possible. Everyday cooling fans are tightly governed. The building management system throttles their speed to meet specific fan power caps, saving every possible watt of electricity. But when an alarm triggers, those green energy targets instantly and unconditionally surrender to life safety survivability. Energy conservation is irrelevant during a fire. This diagram details the command shift. The fire alarm control panel issues a priority 0 command, an unyielding physical override severing normal operational logic. By completely isolating the building management system, this hardwired authority physically stops normal HVAC units, starving the fire of fresh oxygen. The system initiates a run-to-destruction protocol. Energy-saving soft starters are instantly bypassed. The priority is maximum smoke extraction, regardless of wear on the equipment. This mechanical transition is violent during a sudden catastrophic loss of normal utility power. Spinning fans halt. Massive automatic transfer switches violently shift the building load to the emergency bus. The definitive test of a facility's survivability is its mechanical ability to reboot those life safety loads from 0 and explicitly reestablish the correct air paths within exactly 15 seconds of that blackout. True control in a crisis demands completely bypassing everyday software intelligence. The system relies entirely on brute force, hazard-specific hardware logic to protect the occupants. Structural safety in these facilities is a dynamically engineered fluid wall. Looking at this pressure cascade model, the fire floor is a 0 Pascal sink. Extract fans pull air from this zone. Simultaneously, adjacent vestibules are pressurized to 25 pascals, blocking smoke. Finally, staircases receive 50 pascals of continuous pressure, ensuring a clean air escape route. Maintaining this cascade requires precise mass balance logic. The control sequence must account for makeup air, exhaust flow, and the exact architectural leakage across all zones. This critical mass balance must recalculate instantly. The moment of physical boundary changes, like an occupant pushing an egress door open, the system adapts to prevent a pressure collapse. Without continuous, verified mechanical force maintaining this directional fluid wall, vertical cores lose their protection and immediately transform into deadly chimneys. Engineers face a specific physical tension in these spaces. They must pump air pressure high enough to keep toxic smoke out, but keep it low enough so humans can physically push the doors open. This schematic breaks down the maximum allowable door opening limit. The total force required to escape is the sum of the pressure force holding the door shut, plus the mechanical friction of the door closer. Egress calculations cap this strictly at 110 newtons. To stay below this 110 newton limit, leakage calculations and pressure relief vents dynamically size the system. When pressure spikes, relief dampers actuate to vent the excess air. Verifying this delicate balance requires 3 physical tests. Engineers measure the exact force needed to unlatch the door, set it in motion, and push it to a full open position. If a stairwell is overpressurized by even a fraction, the force required to open the door vastly exceeds the human limit. The exact system designed to save occupants physically traps them inside the hazard zone. Proving these systems work relies on the absolute integration rule of commissioning. If any commanded mechanical device lacks independent mechanical feedback, the entire emergency sequence fails. This hierarchy maps the sequence, from L1 submittals to L3 component testing. Padlocks indicate strict stop conditions. Components must be verified before moving forward. The final L5 integrated test forces power loss and open door states simultaneously, ensuring the cascade holds. Passing this rigorous, multi-tiered gauntlet is the only way to mathematically and physically prove a building will survive a catastrophe. A meticulously commissioned system can pass every test, yet still be defeated by a single point of invisible mechanical friction occurring years later. Consider a stairwell pressure relief vent that slowly rusts closed. Under intense internal wind pressure, the heavily corroded steel damper shudders, but fails to actuate. Without that relief path to vent excess air, the internal stairwell pressure rapidly cascades past the 50 pascal limit. Egress doors are instantly pinned shut by the air, requiring vastly more than 110 newtons of force to open. This logic loop illustrates another invisible threat, a digital sensor calibration bias. Here, a differential pressure sensor is reading off by just 8 pascals, injecting an error into the control logic. That minor 8 pascal bias artificially tricks the system into prematurely reducing fan speed. The airflow reverses direction, instantly flooding a protected egress zone with toxic smoke. The system also remains vulnerable to digital conflict if the hardwired separation from the building management system is compromised. Without that physical isolation, a stale energy optimization command can still attempt to throttle fan speeds even while a fire is actively raging. Or there is the risk of a suppression conflict. Triggering a purge fan prematurely vents a clean agent like MVAC 1230 out of the room, completely defeating the chemical hold time required to extinguish the fire. When a physical result fails, operators cannot trust the user interface. They must trigger a strict 5-step diagnostic chain, physically walking the air paths to hunt down the mechanical friction blocking the flow. These single-point failures prove why independent physical verification and hardwired overrides are mandatory. Without them, an invisible fault will trap occupants inside a burning facility. Even after the physical fire is extinguished, the risk remains. The atmospheric toxicity and severe mechanical instability of the equipment present critical, ongoing threats. Prematurely resetting the fire panels invites an uncontrolled automatic restart. Heat-damaged, unstable equipment is violently thrown back into high gear, potentially sparking a secondary disaster. True recovery requires strict protocol. Operators must secure formal release from the local authority, initiate manual purging sequences, and verify atmospheric safety before restoring any normal configurations. During this process, stop work triggers must be strictly obeyed. Any action that leaves a protected zone without approved compensatory measures must immediately halt. The ultimate engineering mandate for these facilities is exact. Design the specific mode, prove the physical airflow, protect the command hierarchy, and permanently preserve the digital evidence. No life safety claim is valid until physical performance is explicitly measured under an approved scenario and mathematically proven to survive its own mechanical failures.